Felix on wave and ray optics for 3D printing, and there's some more in between there. But
Okay, thanks for the introduction. So yeah, as announced, so wave and ray optics for light-based tomographic 3D printing. So I'm Felix. I'm a PhD student at EPFL. Can just want to quickly show the picture. So it's a great place to be. So actually, my building is right here. So I have a view on the lake, view on the Alps. So if you're ever at EPFL, just come by. So yeah, the title mentions 3D printing. It's tomographic 3D printing. Has anyone ever heard about tomographic 3D printing? Okay, actually one person, two person. And so who has a filament printer at home, a 3D printer? Okay, a couple of people. Who has ever tried an SLA printer, so a light-based 3D printer? Okay, a couple of people. And even maybe a DLP printer, also a light-based 3D printer. So all of those technologies, they have a big disadvantage. They do layer by layer, and it usually takes minutes to hours to 3D print something. So what I'm working on is called something light-based tomographic 3D printing, where we don't print layer by layer, but instead we print everything at once in relatively fast speed. So tomographic 3D printing, so usually we use the acronym TVAM. And here I want to show a live video or real speed video of printing a Julia logo. So I just started here, and when you look here, after some time, there's here this gray bar coming. So this is actually UV light coming from the side, and the resin is in this glass vial here, so we rotate this at a moderate speed, so it's still real time. So what the light actually does, the light propagates into the resin, and because of absorption, the light gets absorbed and triggers a chemical reaction. And this chemical reaction needs a bit of energy to really happen. So right now, a lot of radicals are generated, and after a while, there is enough radicals, and then they create the Julia logo, which appears right now. So now the print is actually over. So within 30-40 seconds, we are able to print centimeter structure with an accuracy to right now up to, let's say, 50 or 100 micrometer, which is in terms of voxels per second, one of the fastest 3D printing techniques out there. So just a couple of physical key points, let's say. So TVAM is a single photon absorption technique, like SLA, for example, too. And the resin, it's usually like acrylate resins, and we mix their photoinitiator in there, and the photoinitiator reacts with the UV light to create the radicals. And then the basic setup is like this. So what we have on the left-hand side is here a light modulator. So what we have is we have a powerful laser. It's like a 2-watt laser. So just to mention, a milliwatt can be already dangerous for your eyes. So this is 2,000 times stronger. So even if you put your fingers in there, it kind of hurts. So it gets quite warm. And so we put this UV light source, we shine it on a light modulator. And the modulator is able to essentially project 2D images, like a light projector, in a grayscale manner. And then we have an imaging system here, and the imaging system images the patterns into the resin. And the mathematical assumption what people did in the beginning, and also what we can still do here, is that we assume that the rays are parallel. So we assume they're propagating parallel through, so they are geometric rays. We ignore any effects of, let's say, refraction or even wave optical effects. So the basic assumption, you don't need it. So all the rays are propagating parallelly through. And then the resin we rotate, and then because of the tomographic fashion, we somehow access the 3D space. So if you're familiar with computer tomography, of course, there's a lot of analogy, right? So in CT, in computer tomography, you rotate a patient, and you have like plane waves or straight rays propagating through the patient, and you measure an absorption pattern. So therefore, our theory, of course, is connected to the Radon transform. And the Radon transform is just a fancy word for line integral through an object. So if you have given an object f, what the Radon transform does, it takes your object f, and you measure simply the projection of this object along certain directions. So we can do this for the Julia logo, right? So I just load here the Julia logo, and if I now project the Julia logo, let's say from top to bottom, what I observe, I get something like this, right? So if you project the 2D Julia logo to a 1D line, of course, you get just a 1D function. And it still resembles a bit the Julia logo, right? So you can identify the J, but for example, you're not able to know, or you're not able to distinguish if there is a point on top of the J or not, because everything is just stashed together, right? So you're losing a lot of information. So what you need, so the Radon transform, just a single projection is not enough. What we need to do is we need to collect a couple of them, right? So if I do another angle, then the projection from another angle would look like this. So 2 projections are also not enough. But what happens if I increase the number of projection angles, I get something which is called the sinogram. And the sinogram is again like something, an image. It's an image, but the information is just in a different space, so to say. So we have to we want to revert this. And if you go to CT, like the classical medical CT, what they measure is essentially this. So they have the patient, and what they measure is this. So their task is now, how do I get from the measurement, from the CT measurement, back to the patient, right? So you need something, an algorithm to revert this. And fortunately, there is an algorithm, and it's called the back projection. And the back projection is, again, an integral. And in this integral, what you essentially do is you take your projection and you just smear it back into space. Because in a way, you just forward everything, you stash it together. So if you want to reverse it, you just smear everything back. So let me quickly demonstrate this. So for one pattern, if we do this, what we obtain is something like this, right? So we just smear the pattern back into space. So if we add, of course, this didn't work. I'll have to click on it. Yeah, so if I add another pattern, so this is already 3 patterns from 3 different angles. Now it's 4 different angles, 5 different angles. So I can repeat this procedure. So instead of doing only one projection, I do many projections from many different angles. And if I keep doing this, after a while, you see the Julia logo is coming back, right? It still looks a bit blocky, but if I keep doing this, after a while, it looks better. But let's go to a very high number of angles. So instead of 24, I do 266, and then you see the Julia logo is back. But unfortunately, it looks a bit blurry, right? So since we smear the projections back into space, we just smear everywhere intensity, which is not that great, right? We get only a blurry Julia logo. And in CT, people came up with a clever thing. In CT, they apply a filter, and then this filter somehow magically makes the Julia logo nice again. However, on the computer, you can do this. But in practice, our printer is literally doing this. Our printer has light, and it sends it back into space, right? It back projects it into the space. So the light is putting intensity everywhere. So if we would like to apply this filter here, we would actually need to be able to project negative intensities, right? Because if I smear a bit of light everywhere, I would need to somehow revert it, which only works with negative intensity. But unfortunately, a laser always has positive or greater than 0 intensity, so we can't project negative intensities. So the problem is the filter back projection, which works in CT on the computer perfectly, it does not work in our printer because we can't project negative intensities. So, but fortunately, what saves us a bit is that the resin, as I told you in the beginning, you need to put enough intensity into the resin. If you only put a little bit of light, it won't polymerize. So you really need to put enough intensity. So what we say, the resin has a threshold. So it only polymerizes if it crosses the threshold. So let's hope that maybe the threshold kind of fixes this, right? So we have this blurry Julia logo, right? This one here. So maybe if you apply a threshold function, as the physics does, maybe we get the perfect Julia logo. So if we do so, we see, yes, some of the letters appear, but the center seems to be heavily over-polymerized and the J is not even there, right? So we can play around with it, but there will be no perfect threshold to get the perfect logo. So somehow the naive Radon transform, it does not work. It makes everything blurry and the threshold function doesn't fix it. So yeah, what we have to do, we have to somehow solve an optimization problem. So what we are given is the optimization problem which we want to solve is what are the images I have to put on my projector such that I get what I want to print, right? So what I do, I build a physical model. My physical model is the rays propagate through, and I have the images which I propagate through. So the question is the optimization problem, what are the back projected patterns, so the image on my projector, and if I project them into the space, I want that voxels of the object cross this energy threshold, and voxels of the void region stay below. And that's the only freedom I have. And if I want to phrase this, I can hope that this works with a gradient descent and automatic differentiation approach. So what I do, I write a loss function. So what I just said in Word, I write in different terms. There's one term, it essentially forces that everything of the object polymerizes, so everything of the object receives enough energy. Then there's the second term, which means that everything outside or not the object stays below this energy threshold, and everything else, we want to avoid here over-polymerization. So we want to avoid that some regions get way too much intensity, because then it gets a bit more complicated. So what we do essentially is we build a physical model where the input are our images, and then we apply we propagate everything into the space, we apply the loss function, and then we do gradient descent to optimize what are the patterns we have to put on the detector. So just to summarize the physics again, and then we can dive a little bit into how we did that in Julia. So what we put on the detector, or what we put on the projector, is a 2D patterns. And we have many of those 2D patterns. For each angle, we have a slightly different one. And roughly in our experiments, we project 1,000 images. So it's quite a bit. And then each of those images, they propagate through the resin, right? So for, like, let's say 10 milliseconds, I show pattern A, then I rotate the resin. For another 10 milliseconds, I show pattern B. So all of those patterns, they propagate into the volume. They deposit their intensity, so they put the UV light into the resin. It gets absorbed by the photoinitiator. And all of those patterns, they essentially sum up. So what I get is a summed intensity, which kind of looks like the cross-section of a boat, but only because of the threshold function, which is given by the chemical, physical properties of the resin. Only everything after the thresholding polymerizes, so luckily this threshold saves us, and we get the perfect Banshee boat. And all of this, as I said, there's no layers. Since we have the images, everything is projected at the same time. So we don't do layer by layer, but essentially all the layers are encoded into this image. So all the layers just appear at the same time. So yeah, what we needed. So of course, so this TVAM is a relatively new technique. It's like 3, 4, 5 years ago old. And in the beginning, actually, people, they took the filtered back projection and just clipped it to 0. And they said, yeah, it kind of works. But if you look at the edges, it doesn't work that well. So what people developed more recently is that they do gradient descent based schemes. So what we needed in Julia, clearly we needed good optimizers. So there's a couple of packages. I use usually Optim.jl, because when I started using Optim.jl, there was no optimization.jl. For automatic differentiation, I'm still using Zygote. Of course, Enzyme would be nice to try, but I used differentiation interface, and Zygote did not work in our case yet, so I'm still using Zygote. And we definitely needed CUDA support because we do big optimizations. So just written down here, so as a rough estimate, so the patterns we optimize are HD resolution, so it's 1,000 times 700 roughly, and we have 1,000 angles. So if you multiply this together, you end up with almost 1 billion parameters to optimize. Just to store those billion parameters and doing one forward pass is usually gigabytes of memory already on the GPU. So this is a very big optimization problem. And further, what is kind of a bit also tough is that the 3D Radon transform has a computational complexity of n cubed times the number of angles. So it's essentially n to the power of 4. So 1,000 times to the power of 4 is a very big number. So even on the GPU, this takes some time. So on the biggest GPUs you can get, it takes like, I don't know, for this realistic volume, like, I don't know, 5-10 minutes. And later on, I want to show a bit the wave optical stuff, because as I said, right now everything so far was explained from the ray optical perspective. So what we wanted to have this ray optical propagation scheme to propagate the rays back into the volume. But at some point, you also want to use wave optics, because when you go to small scales, ray optics is not quite valid, so you have to use a new physics. So those were the parts we had to create. So a little bit of ray optics and actually more of the wave optics part. So one package which serves essentially as the backbone for the ray optical parts is RadonKA, which is essentially a very simple Radon transform implemented with kernel abstractions. So it's like 300 lines of code, and it provides routines for 2D arrays and 3D arrays. And the standard Radon transform, which a lot of people use, for example, Matlab, is just the parallel Radon transform and the back project. So essentially the two functions we also need. And more notably, like for the printer, it's not quite the Radon transform. Mathematically, it's the attenuated Radon transform, because when the light propagates into the resin, the ray gets absorbed, right? It loses a little bit of intensity. So the mathematical correct term is the attenuated Radon transform. And if you Google this, there is no implementation in any of the languages. So no one's using an attenuated Radon transform. So you can do a hacky version of it, but then it's very slow and very memory intensive. So we also had to implement this attenuated Radon transform. And in a way, what's pretty cool is that everything is essentially a very flexible attenuated Radon transform. And if I don't use the attenuation, you simply set the exponential factor to 0, and then nothing happens. So in a way, RadonKA is a very flexible package. And even though it's very flexible, it still can compete with ASTRA, which is a very common CT library. And it also beats Matlab if you use CUDA, because Radon on CUDA and Matlab doesn't work. Or it's not very fast. It works, but it's very slow. Just to show a bit the flexibility of Radon. So with RadonKA, I can essentially specify what geometry I have. For example, in this case, it's a parallel geometry. This is called the parallel Radon transform. However, sometimes I I don't have parallel rays, I have some rays which are bent, then this is called like cone or fan beam tomography, so I can just specify that, and at the end everything runs very well. And then actually in our printer, we use more often this cone tomography because if the rays hit our round glass vial, they actually get refracted. So they're not propagating parallel through the resin, but instead they're getting refracted towards the center. So most of the time I'm actually using this one. And it's so flexible, then you can also play around with, I don't know, to do very funky geometries, which none of any other packages I've ever seen supports this. So for us, this is very flexible. And also the good thing is if I run this on CPU, right, I can just run it. It's multi-threaded on like 24 cores, but if I run it on a GPU, it's much faster. So in this case, I don't know, 30 times or 20 times faster. So that was really important for us that the CUDA performance is good because we have the big volumes. So we needed this performance. And this is all implemented in kernel abstractions. I can just highly recommend this package. Very easy to use and very great performance. I mean, I'm not a CUDA expert at all. I'm just using it, but it just works. Another package we implemented, then more tailored around the problem of TVAM, is called SwissVAMyKnife, and it's the only toolbox I need for tomographic printing. And it can include the physical properties as the absorption of the resin, because if I put more photoinitiator, I have more absorption. If I put less photoinitiator, I have less absorption, but then I also need to print longer because I need more time to accumulate all the intensity. It supports different geometries and also ray and wave optics. And the way it works, from the user point of view, in the beginning you would just specify your target geometry. So in this case I want to print the Julia logo, so I specify the 3D target geometry. What I show here is just one of the cross sections. Then I define the loss function as I explained in the beginning, so I have this thresholding of the different terms, so I just define it here. Then I define my optimizer. In this case it's gradient based. We also offer some iterative methods, but most of the time I'm using gradient based with an LBFGS optimizer, 15 iterations, that's good enough. Then I need to specify the angles, right? Because depending on how much I rotate, I'm able to show more angles or less angles. I specify my geometry, especially this is a very critical parameter, the absorption of the resin. And at the end, I just call optimize and it will optimize it. And what I can do, so for example, what I'm showing here is that would be the final patterns I would show on my projector. So we can look at them from different directions, and you see it looks kind of like the Julia logo, right? So it's usually you can interpret those patterns very well, but to calculate, especially here, sometimes you see at the edges, yeah, to really get the precise intensities, you have to optimize it. So there's no way you can avoid this. Another funny physical effect is if I increase the absorption quite a bit, what happens physically is that the light, it propagates through the resin, but it doesn't reach the center because it gets absorbed on the outer region. So the red region means a lot of light is deposited. So in practice, if you put too much photoinitiator, you can't print because your light already gets absorbed on the outer shell of the glass vial. And this is actually what they do in an SLA printer. In an SLA printer, they put a lot of photoinitiator into the resin because they print layer by layer, and they want that the light doesn't propagate deep. They want that the light essentially gets absorbed in the very thin layer at the top. So that's why they put a lot of photoinitiator in their resin. And in our case, we do like really a lot less, like, I don't know, 3 or 2 orders of magnitudes less in photoinitiator to avoid that, because we want that the light propagates through the resin. Yeah, exactly. So this is all the ray optical part, but of course, I mean, this ray optical part people did before, so this is kind of reproducing existing science. So what I did in my PhD, we were like, thinking about, okay, let's try to push the resolution of those printers, because 150 micrometer is great, but there's printing technologies which can print 100 nanometers. So can we push in this direction? And for that, we developed a wave optical framework, and of course, we needed it to be differentiable. As I explained in the beginning, all the optimization is based on gradients, so we needed a physical model, a wave optical model, which we can differentiate through. And for that, we created the package WaveOpticsPropagation, which provides the routines for free space wave propagation. And if you ever worked with wave optics is way more expensive than ray optics, because in ray optics, the rays, they just propagate through and they don't talk to each other. But in wave optics, everything talks to each other. Like in wave optics, their borders, they morph to each other, you have diffraction effects and stuff like this, and those are global effects, so the pixels have to talk to each other. And what you use in the backend is like FFTs all over the place. So we use a lot of FFTs, and to avoid that this is very slow, we also had to create a lot of memory buffers. So to use the wave optics propagation, what you usually do is you create a type where it essentially stores a lot of buffers, it stores all the information, it pre-plans the FFTs, and you do this only once, and once you call it, you just run it, and then it executes the wave optical simulation. And this is a bit of a pain. I have to say in Julia it's a bit of a pain because to get it fast you have to use the memory buffers, but then automatic differentiation with SIGO doesn't work anymore because it's in-place mutation. So essentially we had to write a lot of the gradient rules ourselves. So, and I know a lot of people in our field, they're just using Jax or PyTorch, and it just works a bit better, honestly, there. So it's a bit of a pain, but at the end it kind of paid out. So because we could also make, actually an algorithmic improvement on the backpropagation. So at the end I actually needed chain rules to make also the algorithms better. So I couldn't avoid it anyway, but it was a bit more painful. And what I can just, so what I can do here is I can simply compare the wave optical part and the ray optical part. So what you see at the top, at the bottom, that's the easy one. That's the one we discussed in the beginning. That's ray optics. So the ray optics just propagates through the resin, and the rays just are straight. There's no way that they deflect or whatsoever. But in wave optics, if you propagate a wave through a resin, what you see is that the edges they slowly morph, right? So in the beginning it is a sharp edge, but then after a while it kind of blurs out. And the cool thing is, if we now compare this, like our ray optical and wave optical simulation, so the top part is just L here is 10 millimeters. So if I want to print a boat with 10 millimeters, if I look at the ray optical simulation and the wave optical simulation, they both give the same result because in the limit of large structures, wave optical and ray opticals are the same. So that's good. It's a good check that everything works. But if we go to smaller structures, for example, a boat of 1 millimeter or a boat of 100 micrometer, so 10 times smaller, you see at 1 millimeter already that the ray optics starts to fail. So some of the features are missing. And if you go to the very small scale, like 100 micrometer, you see that ray optics is simply it's not the correct physics anymore. So this is all simulation. It's not proven experiment yet, but it's clear. At some point, ray optics is not correct anymore. But what's the cool thing is that if you use the correct physical model and you optimize the patterns with the correct physical model, it shows that in theory, it's still possible to print in the region of this, it's a 100 micrometer boat, but the features are much smaller. They're like 10, 20 micrometer or even less. So if you use the right physical model and you just optimize the patterns on the right physical model, you are able to print much smaller features. I just skip over this part. So at the end, I just want to summarize with our packages. Essentially, SwissVAMyKnife, RadonKA, and WaveOptics, we could essentially show that TVAM is able to print at small structures, and we had to develop quite a bit to be able to show so. And I really want to give a shout out to some of the packages, especially kernel abstractions. It's really great for RadonKA. It's amazing for me to use, and it's a lot of fun to write and very easy to write. That's it, and I'm looking forward to your question.
So, any questions? Yep.
Yeah, really cool, thanks. So with the extra work you had to do to get AutoDiff to work, have you now fixed it for everyone, or is this like an ongoing problem? Are people going to have to keep adding to that?
So I think it's just the fix for me for the wave optical stuff. So it's just in my package that I registered a custom reverse rule and to fix essentially my forward pass.
So what things did you have to add rules for?
So like I think I have the code here. So the problem is really like my forward pass looks like this. So I use essentially existing buffers, I do a bunch of FFTs, I shift them around, and everything is in place to not allocate a lot of memory. And SIGO on this immediately fails, right? All of this is in place. And then I tried with differentiation interface enzyme, and it gave up. So I think that the problem is really the in-place mutations all over the place. Like IFFT shift, I do multiplications, and even the FFT isn't in place. So really, so this line of code actually, it only allocates once at the very end where return a new array, which is just a new, not a view, but a proper copy. So and this part of, so essentially for this, I had to rewrite the reverse rules myself.
Yeah, I suspect that enzyme struggles with the FFTs because I imagine that you're just calling the FFT library or the CUDA one or the...
Yeah, probably. Yeah, so I'm also not sure because in this case I'm using complex numbers, CUDA, and FFT. So I mean, it's a lot of knowledge. I think, there's a question over there.
I guess you assume coherent wavelength everywhere?
Yeah, so for the wave optical simulation, that's all coherent, yeah. So in
And you kind of show that because you're using a laser, right?
So actually, so that's why it makes it difficult to do that in experiments, because we are using a DMD, which actually does not a grayscale modulation, but it does a time-modulated grayscale modulation. So with our setup right now, I can't use my theory, because the setup, what we do, it actually would require a binary optimization. So it's a bit tricky. So you could implement this with different hardware devices, but then at some point you realize the glass vials, the best accuracy you can get for glass vials in precision of the wall diameter is like 100 micrometer, 10 micrometer maybe, but if you want to print at 1 micrometer, your glass vial is simply not good enough. So it really is an engineering problem that our round glass vials are not precise enough to use that theory. So we really struggle that our hardware is not good enough for the theory we would like to use.
Thank you.
I think one more over there.
Thank you very much for your wonderful presentation. Could you please give more details of how you use the kernel abstractions to implement the Radon transform?
So I think the Radon transform might be a bit too much, but I have an example on the differentiable image rotation. So there was also no differentiable image rotation in Julia, but we just implemented one on the way. And kernel abstraction is very easy. So you have a normal function. So the imrotate, you would give it an array and an angle. And at the end, for the kernel abstractions, you need to require backend, which in this case depends on if it's a CUDA array or normal array. And then you have this kernel. And the kernel is essentially called here. And what I do in this case, instead of having two for loops where you essentially have a for loop for j and for I, instead you have this kernel abstraction specific statement where you essentially extract the I and the j, and then you just run your kernel. And that's it. So essentially transforming your code, instead of using 2 or 3 nested for loops, so in my case they're all independent of each other, so you can parallelize it. Instead of using those 2, 3 nested for loops, you use kernel abstractions, you put this statement, and that's it. So it's very easy. So I really recommend to check out the documentation of kernel abstractions. It makes the life very easy. And it runs on GPUs, CPUs, technically also metal GPUs. However, we tried last night, didn't work. But yeah.
Thank you.
I think there's one question.
Out of curiosity, on your experiments, how is like work holding happen for something? Because I imagine you have your resin in a vial or something, and how do you hold the piece of work?
So essentially everything is embedded in the resin, and so for that we have a drill bit holder. So the vial is it's 16 millimeters in diameter, so it's a small glass vial. We essentially put it into our drill bit holder, we fix it, and then we just rotate our stage. So if you're interested, there's also a paper from another group where they assembled this for like $500. So it can be done relatively cheap, but yeah, it's a bit technical. It's not as easy as a SLA printer, and the community is not as big. There's also some companies popping up right now, but yeah. So technically, you can build one yourself for like maybe 500. But you also need some light source. But you don't need a laser. You can also use a high power LED, but still watch out for your eyes. So it's dangerous. You mean a printer or a printed thing? The printed thing is actually, so it's very small. So and also so printing the Julia thing is not quite impressive because it's a disconnected thing. So if you print it, you just have all the letters all over the place. And also it's very small. So I should have given you some boats, but the thing we're talking about, it's small. So it's not very impressive and it's also a bit sticky, and sometimes the things we use, they cause cancer, so. But we can actually do bioprinting. So if you're in biology, and one of the big and promising applications of this printer is actually bioprinting. So recently in our lab, we printed parts of a pancreas, like parts of the human pancreas with cancer cells, and then you can do 3D studies of cancer growth and stuff like this. So bioprinting seems to be one of the promising applications, but also optical components and stuff. So yeah, the technique is relatively new, so there's more and more applications popping up.
All right, thank you.
Thanks a lot.